Hi, in this video, we're going to continue our course on polynomials and we're going to talk about roots of polynomials. So I wanted to make a few points regarding the theory here. So the first thing is, if a non-real complex number z is a root of a polynomial px, polynomial p of x with real coefficients, then z conjugate is also a root of p of x. This is like saying that if a polynomial p of x has real coefficients, then the imaginary roots will come in pairs. Pairs like z and z conjugate. Both of them will be roots. The reason for that is because of Vieta's relations, the sum of the roots and the product of the roots have to be completely real in case the coefficients of p of x are fully real. So sum of the roots and product of the roots, if they are real, that can only happen if the complex roots of p of x are conjugates of each other. So basically what we can say here is that p of x is divisible by x minus z times x minus z conjugate. Basically, if x minus z is a factor of p of x, then x minus z conjugate is also a factor. So p of x will be divisible by the product of these two, right? So this product, if you calculate, it is x squared minus x z plus z conjugate plus z times z conjugate, which is same as x squared minus 2 times real part of z times x plus mod z squared. So p of x will be divisible by this quadratic factor. This is the case when p of x has real coefficients and has a complex root z. We can say that it will be divisible by this quadratic factor. So keep this in mind. This will be useful in problems. For example, let's try this particular question. The question states that let f of x, g of x, h of x, and k of x be polynomials such that which satisfy these two relations, x squared plus 1 times h of x plus x minus 1 times f of x plus x minus 2 times g of x equals 0, and also x squared plus 1 times k of x plus x plus 1 times f of x plus x plus 2 times g of x equals 0 for all x belongs to complex numbers. Now we have to prove that f of x and g of x are divisible by x squared plus 1. Are divisible by x squared plus 1. Right. So there are four polynomials f, g, h, and k which satisfy these two relations for all x belongs to complex numbers, and we have to show that f of x and g of x are divisible by x squared plus 1. Right? Now, in order to show that it is divisible by this factor, x squared plus 1 is a quadratic factor, so that means x squared plus 1 could be written as x squared minus I squared, which is x plus I and x minus I. So what we have to prove is fx and gx are divisible by x plus I times x minus I, which means you have to find out whether f of I and f of minus I are equal to 0 or not, right? If f of I is 0 and f of minus I is 0, then x plus I and x minus I are both factors of f of x. This is by factor theorem. Similarly, if g of I and g of minus I is 0, then g of x will be divisible by x plus I and x minus I. So basically, we have to use these two relations to find out somehow what is f of I, f of minus I, g of I, and g of minus I. And hopefully, if all four of these things are equal to 0, we'll be able to say that fx and g of x has factors x plus I and x minus I. And the question will be done. So now actually it is pretty simple how to check this, because if you put x is equal to I in the two relations that are given to us. So let's put x is equal to I here. X is equal to I in this relation. You get this part will vanish because I square plus 1 is 0. You will get I minus 1 f of I plus I minus 2 g of I equals 0. And in the second one, you get I plus 1 f of I plus I plus 2 g of I equals to 0. Now, these two equations are like two equations with two unknowns. What are the unknowns? F of I and g of I. We can easily solve these two equations, and you solve it for f of I and g of I. When you solve it, what you have to do is basically do simple simultaneous equations and solve it. You will realize that f of I is equal to g of I is equal to 0. This will come after you solve it. And that will mean that x minus I is a factor for both f of x and g of x, right? Similarly, how do we check the other thing? We put x is equal to minus I in the same two relations, right? We put x is equal to minus I here. You get minus of I minus 1 times f of I minus I plus minus I minus 2 times g of minus I is 0. And similarly, you get another relation from here. You solve it again and find out the values of f of minus I and g of minus I. It will turn out that both of them are also 0. And therefore, then what it means is that x plus I is also a factor. So since x minus I and x plus I are both factors of f of x and g of x, we get the proof that the two polynomials f of x and g of x are divisible by x squared plus 1. So I will leave it to you to work out the details. The idea is pretty simple. Let's look at another question. This question says, let p of x be equal to x power 4 plus 14x cubed plus 52x squared plus 56x plus 16. And what we have to do is analyze this polynomial and figure out information about its roots or nature of the roots of this polynomial. So consider this sort of a theoretical lesson which reviews what we have done so far in the course. Basically, we have learned reciprocal polynomials in the previous section, and now we are looking at complex numbers and polynomials here. So I'll apply the concepts of those sections that we have already done to analyze this particular function. So what you can say here is, let's try to think of the polynomial q of x. Q of x is given by 1 by 16 of p of 2 of x. Let's try to evaluate what this comes out to be. Okay, so it is 1 by 16. P of 2 of x would be, if you put 2 of x here, you will get 16x power 4 plus 14 into 8x cube plus 52 into 4x square plus 56 into 2x plus 16. What is this inside part? This is p of 2 of x, right? So when you calculate it out, you will realize that q of x will come out to be x power 4 plus 14 into 8 by 16 will be 7x cube plus this will be 13x square plus this will be 7x plus 1. So we are getting q of x like this. And notice one nice thing about q of x. The coefficients of q of x are following the symmetric pattern 1, 7, 13, 7, 1. So we know that q of x is a reciprocal, self-reciprocal polynomial, right? From the previous videos, you know what is a self-reciprocal polynomial. The coefficients of the polynomial are symmetric from both the ends, right? So if q of x is a self-reciprocal polynomial, we know that its roots will be of the form t and 1 by t. Roots will come in pairs for q of x, right? Now think about it. If r is a root of p of x, right? Then if we set x is equal to r by 2 in this relation, what will I get? Q of r by 2 is equal to 1 by 16 p of 2 times r by 2, which is 1 by 16 p of r. And now p of r is 0 because r is the root of p of x. So this is 0. So we are getting if r is a root of p of x, we got that q of r by 2 is equal to 0. Therefore, r by 2 is a root of q of x, right? Because p of x 1 by 6, we had q of x was equal to 1 by 16 p of 2x, right? Q of x was 1 by 16 p of 2x. From here we are deducing this. So if r by 2 is a root of q of x, then 2 by r is also a root of q of x. Also a root of q of x, which means because of the fact that q of x is self-reciprocal, the roots of the reciprocal polynomial will be reciprocals of each other. If r by 2 is a root, then 2 by r is a root of q of x. Now that implies that q of 2 by r is equal to 0, and that means in this relation, if I put 2 by r, we get 2 by r is equal to 1 by 16 p of 4 by r. So since this is 0, that means that p of 4 by r is equal to 0. So therefore, 4 by r is a root of p of x. So notice how the fact that we have constructed the reciprocal polynomial is coming in very handy for us. We are getting that if r is a root of p of x, we have gotten 4 by r is a root of p of x also, right? Now, what you can do here is look at the p of x polynomial now. P of x polynomial was x power 4 plus 14x cube plus 52x square plus 56x plus 16, and we have gotten that r and 4 by r are roots of p of x, right? Now we will take advantage of the property that a polynomial is always continuous. So if you check the values of the polynomial, p of 0 is 16, p of minus 1 is minus 1, and p of minus 2 is actually plus 16. So if you think about it, 0 is here, minus 1 is here, minus 2 is here. The polynomial is positive at minus 2, but it is negative at minus 1, and then it is again positive here. So we know for sure that the polynomial is changing sign between minus 2 and minus 1 and between minus 1 and 0. So obviously one root will be between these two numbers and one root will be between these two numbers, right? Now think about it. We already know that r and 4, if r is a root, then 4 by r is a root. So if alpha is a root, then 4 by alpha is also a root. And similarly, if beta is a root, then 4 by beta is also a root, right? Since we have two roots of the polynomial between -1 and -2, -1 and -2, and between 0 and -1, there are other two roots also, 4 by alpha and 4 by beta also have to be there, right? Because of the result that we have figured out. So now you realize that all the four roots of the polynomial have to be negative. All four roots of the polynomial, alpha, beta, 4 by alpha, 4 by beta, are negative, right? And notice that the product of the roots is coming out to be 16. Minus plus minus. This should have come out as 16, right? Correct? So basically we have found out many things about the particular polynomial. You can also try and figure out what the roots will be based on the Vieta's relations here. You have 14, 52 and 56 here. So you should say alpha plus beta plus 4 by alpha plus 4 by beta is equal to 14 minus 14. And similarly, you can try and solve, when you take 2 at a time, you'll get alpha, you'll get 6 terms there, should be equal to 52, right? You can try and figure out the roots also. We have already done majority of the analysis because we have figured out that all four roots are going to be negative, and also roots are of the form alpha, beta, 4 by alpha, 4 by beta. Okay? And the key point in doing this analysis was analyzing the QX polynomial, where we said QX was equal to 1 by 16 P of 2x, and QX was a self-reciprocal polynomial. So that helped us in figuring out what is happening here. So the rest of the part, finding out alpha and beta, I will leave it to you. You have to use Vieta's relations along with the information we have deduced so far to find out the roots of this polynomial. Let's go on to the next one. Next question says that find the sum of the moduli of the roots of polynomial p of x, which is equal to 20x power 8 plus 7i x power 7 minus 7ix plus 20. So possibly there are going to be 8 complex roots for this. This is a polynomial with complex coefficients. So in general, there will be complex roots, and there will be 8 of them by the fundamental theorem of algebra. You have to find the modulus of, you have to find the product of the moduli. So actually it's not the sum of the moduli, we have to find the product of the moduli of the roots of this equation. We have to find mod of z1, z2 till mod of z8. If z1, z2, z8 are the 8 roots of this polynomial, right? So let's try to analyze what we can do here. So if R is a root, then obviously P of R is equal to 0. And let's try to see, notice one thing, 20 and 20 and 7i and 7i, it seems like it is some sort of a reciprocal polynomial situation, right? So if you calculate P of R by R power 4, that comes out to be 20 R power 4 plus 7i R cube minus 7i by R cube plus 20 by R power 4, and this can be written as 20 R power 4 plus 1 by R power 4 plus 7i R cube minus 1 by R cube, right? This is the value of P of R by R power 4. Now let's assume R is imaginary. R is given by IT. Let's say it is a purely imaginary sort of root, right? If you assume R is IT where T is real, then we get P of IT by I power 4 T power 4 is equal to, if you put r as it, you will get t power 4 plus 1 by t power 4. Put r as it, you will realize that this will be simplified as minus 7 I square t cube plus 1 by t cube. And I square is minus 1. So what we get is basically t of it by t power 4 is coming out to be 20 t power 4 plus 1 by t power 4 plus 7 t cube plus 1 by t cube. Here we have assumed that r, which was a root, is a complex number of the form it, where t is real, right? And this is what we are getting. Now, we know that r is a root, so this part is simply p of r by r power 4. So the left hand side is 0. So 0 is equal to, you are getting 20 t power 4 plus 1 by t power 4 plus 7 t cube plus 1 by t cube. Now, if you do the substitution, y is equal to t plus 1 by t, you will be able to express t power 4 plus 1 by t power 4, and this in terms of y. You can write 20, this will be y square minus 2 whole square minus 2 plus 7 y cube minus 3y. And if you simplify it, you will get this equation. 0 is equal to 20 y power 4 plus 7 y cube minus 80 y square minus 21 y plus 40. This is my equation in y. And you will realize, if you think of this part as your polynomial q of y, you can put the values of the polynomial at 0 at different points. So q of minus 2 will be positive, q of minus 1 is less than 0, q of 0 is greater than 0, q of 1 is less than 0, and finally q of 2 is greater than 0. You should check all of these values for q. This implies that the sign of the q function is changing many times between minus 2 and 2. So you should realize also that q of y is a degree 4 polynomial. Q of y is a degree 4 polynomial, and here the sign is changing 4 times. Once here, then from here to here once, then from here to here once, and then finally from here to. So there are 4 roots of q of y. 4 roots of q of y equal to 0 in minus 2 to 2. Now, if y is one of these roots, if y is one of these roots, then we know that t values, we had done this substitution, t plus 1 by t is equal to y, and this equation becomes t square minus yt plus 1 equals 0. Then t is equal to y by 2 plus minus I times root over 1 minus y square by 4 by the quadratic formula. So if y is one of these roots, one of these 4 roots, right, then t will be equal to this. And notice that modulus of t was equal to root over y square by 4 plus 1 minus y square by 4. So modulus of t is 1. So for each y, we get two values of t, both of which have modulus equal to 1, right? And therefore, for every y, we get two values of t, and there are 4 y roots, right? 4 roots of q of y we got in minus 2 to 2. Therefore, there are 8 roots of t, 8 roots for t that we are getting, right? Where once you get 8 different values of t, you can say our roots are r is equal to it, right? And if r is equal to it is my root, we have found 8 different values of t. So we have found 8 roots of our original 8 degree polynomial, right? Since p of x, the original polynomial, had degree 8, these are the only possible roots, right? There is no other possible roots because we have found 8 roots 8 values of t. And therefore, the sum of modulus of the roots, modulus of each of these roots, t1, it1 plus it2, so on, plus it8 is going to be 8 because each of these roots has modulus 1. We have seen here the roots have mod t is equal to 1. So the sum of the modulus of all of these roots is going to be 8, which is what the question was asking us in the beginning. So basically we have figured out the nature of the roots of this polynomial by thinking about the substitution y is equal to t plus 1 by t. We took the condition that r is equal to it is an imaginary root of the original 8-degree polynomial. The reason we divided by r power 4 was because we wanted to use the reciprocal polynomial properties and express the whole polynomial in terms of t power 4 plus 1 by t power 4, t cube plus 1 by t cube, and so on. That helped us use the substitution y is equal to t plus 1 by t. So I hope you have understood something from this video. I just wanted to share these quick points about roots of polynomials. In the next class, we'll look at more problems which will cover further details and nuances of problem solving in this polynomial section. So if you like the content, please subscribe to the channel and make sure that you share it with your friends. Comment on the videos if you have something to ask, and we'll discuss it in the future classes. See you next time.